So the final speaker for this particular session is Max Raginsky. Max, a long-term Illinois resident, he went to school here, faculty member here. He's also held positions in Northwestern and Duke before coming back to UIUC. Take it away, Max.
All right. Thank you for the invitation. And I didn't go to school here. I was a Beckman Fellow here, but otherwise accurate. Yeah, I'm a long time. I'm a regular. Anyway, so this is entitled On Theoretical Foundations of Diffusion Models. You're not going to hear much about denoising diffusion models, because part of the talk is about some work done in my research group 4 years ago in 2019 on a very simple version of diffusion models. But the question was, what are they capable of? What kind of distributions can we generate? Can we do it efficiently, etc.? And the second part of the talk is about the use of diffusion models instead of sampling to generate random functions of the initial condition. So, and that goes along with classical perspective on diffusions, starting with the work of Norbert Wiener on the Brownian motion, that you can view these processes as random functions. Anyway, so this work is based on joint work with two amazing individuals, Belinda Tsen, who graduated last year from my group with a Ph.D. in computer science. Now she's a postdoctoral fellow at Columbia University in the Department of Statistics, and Tanya Viravalli, who's a member of my research group right now and should be graduating in about a year. So this is some generalities. So we all know this whole message about generative models, but just to set the stage, when we talk about a generative model, we typically have in mind some latent object and some visible or observed object Y, and the generative model specifies their joint distribution. But then, of course, we talk about deep generative models. What do we mean by that? Well, I'm reasonably old to remember that we used to call these things non-homogeneous Markov chains, and now they're called deep generative models. But the idea is that instead of generating one latent object, you generate a whole chain of them using some Markov mechanism, and then the Markov structure means that each object in the latent trajectory is generated based only on the one preceding it. And then at the end of this process, you generate your observed variable, right? So here the idea is that you stop after k steps, and then you generate your y, right? So the question of why we should even be doing something like this, I think there are a number of answers. One is computational. We can actually build quite a variety of various complex objects using very simple steps. For example, we could just take each update to be Gaussian, conditionally on the previous latent state, but the mean and the covariance function of that Gaussian could be some nonlinear functions with parameters of that previous state. And so this functional parameterization allows you to do things like gradient descent, backprop, etc. Right, and generally, this precise idea seems to be one of the drivers of the success of denoising diffusion models. That both the forward process that degrades your target distribution to pure noise and the reverse process that restores it are compositions of simple steps that can be easily parameterized, and therefore, once you have their computation graphs down, you can perform gradient descent and backprop. Right, and like I said, most of the work on this focuses on using this as a sampling mechanism, right? What you're doing is you're generating samples from some complicated distributions, but you can also think about this as a mechanism for generating random functions of the initial condition. And so these two questions of probabilistic generation and random function generation will be the subject of this talk. Okay, so let's first I just want to make sure that my time usage is good. So let's first formalize what's going on. How do we end up with diffusions in the first place? Well, we can imagine a large number of steps where we can, talk about hidden layers, and we sample a bunch of independent Gaussians. So here the idea is that we have these IID samples from a Gaussian on D dimension. Gamma D is a notation for standard Gaussian distribution on RD. And we run this in multiple steps. We start from the initial condition, add to it some mean, and so shift the mean according to some function b of a parameter theta, and then we also add some Gaussian noise. Notice here eta is a small time step, and the mean is scaled by eta, and the variance is also scaled by eta. And we keep iterating this, and then eventually we stop, right? And so this is also one of my Gen X references. It's a reference to this TV show called Daria. My daughter is named Daria, so I have to make that reference. Anyway, so the point is that you by iterating these very, very simple transformations, you can come up with a very rich class of generative models. So when you take, and you have to spend some time making this rigorous, but heuristically, if you consider the case when the step size is very small, and you scale it just right, you end up with a continuous time object here, right? So you have a diffusion process, which is definition of that as a continuous Markov process with certain characteristics that depend only on the first and second order statistics. But the point is that you can describe it by a stochastic differential equation. This is an Ito integral where you integrate a process against Brownian motion, and you run this for some finite time, let's say 1 second or whatever, some wall clock type time, and then you end up with a final sample. Right, and again, you can view this in two different ways. One is a way of sampling. So, for example, if this Q is just the Dirac delta sitting at x1, so you end up with the final sample. This is what you would get in denoising diffusions. Or, like I said, you can think about this as a random function, because its x can be deterministic. This is your input. Think about a neural net, right? With
people online can't hear you. I'm going to give you a lapel.
Oh, because I don't like to be standing here.
Well, if you want to move around, we need this.
Okay.
So, no worries.
All right, this is much better. Sorry, I feel so stifled when I just stand there. Right. Okay. So this is the idea here. Like I said, you can view this in two different ways. One is as a way of generating samples from distributions, and the other one is as generating functions of x. And in that case, that would be just a straightforward neural net with some random activations. Okay, so there'll be two parts. Part one is sampling, and this is based on a paper with Belinda. Like I said, the year is 2019. And the title is Theoretical Guarantees for Sampling and Inference in Generative Models with Latent Diffusions. So as you can see, all of the words are there, but I'm a theorist. I'm very bad at marketing. So if I had used the words diffusion models in this title, who knows? But I didn't. Anyway, so here's the idea. So you can think about this process of generating distributions of sampling from some distribution as a control problem. And there's a lot of math in this, but it's actually very easy to explain what's going on. So let's suppose I have some reference diffusion process. This is given to you. This is something that has been designed, and it just does its thing for some finite time. And you can add a control, which basically all it really does is shifts the mean, right? If you once again think about this in discrete time, very, very short periods of time that you have these Gaussian updates, all you're doing is you shift the mean, right? So the function that allows you to shift the mean is called the control, because what you're doing is you're controlling the evolution of this diffusion process. And obviously when you're doing control, a lot of times what's going to happen is you have a task in mind. Typically, you want to arrive at some state that has high value or low cost or something like that. But then you also want to penalize the effort in getting there. So this notion of cost formalizes that this is the control cost. So think about this as energy that you expend in trying to steer this diffusion process. And this is the terminal cost. And notice that here I wrote this as negative log of some function g. and this function g is supposed to be well behaved for this negative log to be well defined. Okay. Right. So the claim of this work was that this perspective actually gives you both sampling, so you can basically use this control U to shape the distribution of this process at time 1, and inference when you are given samples and you want to infer something about, let's say, this latent object. So you do maximum likelihood, and obviously doing this in diffusions is complicated. So instead you come up with a variational bound. So long story short, the result looked like this. So you can actually quantify the minimum total control cost, right? So remember that you have this reference process, reference diffusion, that think about it as a control-free object. And for that, we assume we can compute its transition function, so we can compute this conditional expectation. And the minimum cost that we could achieve with any control subject to appropriate regularity conditions is negative log of this expectation of g of x1 given x0. So x0 is the initial condition, the starting point, and g of x1 is this cost at time 1. And in fact, we can compute the optimal control u star exactly. It's and this is given by negative gradient of something called the value function, this vxt. Is a solution of a certain partial differential equation, which essentially is a continuous time version of dynamic programming. So this is called the Hamilton-Jacobi-Bellman equation, and this vxt is actually defined as negative log of. So this is once again done with reference to this process without a control. So this one you can I assume that you can compute these conditional densities. And so really, I mean, this was just a synthesis of some existing results, for example, 1989 result of Michele-Pavon, which basically, so that paper from 1989, if you read it carefully, it more or less contains all of the results on the denoising diffusions in it. And everything has been more or less rediscovered. And Paolo Di Prato followed up on this in 1991. And really, like I said, for those of you who are interested, it's in the paper, but the proof relies on 2 probabilistic representations of this object. One is something called the Feynman-Kautz formula that has to do with, it relates solutions of certain PDEs to expectations of certain functions using diffusion processes. And the other one is this Hamilton-Jacobi-Bellman equation, which is, like I said, a partial differential equation for the value function of a stochastic control problem. Here, the value function is basically the minimum cost starting from a given initial condition X. Okay, so again, it's a lot of math. And in this paper in 2019, we only considered a very simple case where I want to generate a sample from some distribution mu, let's say, starting from the origin. So instead of saying, oh, I'm going to take a sample from a Gaussian and then gradually shape it to give me a sample from my target distribution, we said, okay, let's instead consider, instead of like a maximum sort of white noise picture, let's consider a, just completely dark image, and from that we're going to build up our target sample. Of course, and then you can actually the denoising diffusion can be represented in this way as well. But anyway, I mean, this was the idea is, like I said, it has to do with a certain free energy minimization. If you've done variational Bayes, this should be no surprise. But the idea is precisely to think about each choice of a control as affecting the distribution of this path, right? Because your diffusion process is a random path, right? On a time interval from 0 to 1, wandering around an RD, and P0 is the law of the reference diffusion. So think about 0 as no control, right? If U is equal to 0 in here, you just have the reference process, right? If you have a control, then you shift the distribution somehow. And in the context of diffusions, there's this wonderful result due to Igor Girsanov that basically allows you to write down the likelihood ratio for 2 diffusion processes that have the same diffusion coefficient. So the object in front of the Brownian noise is the same, Brownian motion is the same, but differ in their mean, the drift. And it turns out that the KL divergence between any controlled process and the uncontrolled counterpart is exactly the expected value of the control effort needed to take one of them into the other. I just want to make sure how I'm doing on time. Perfect. Okay. All right. So the control just introduces the change of drift. And then we can talk about the free energy. So the control cost that I talked about before, this one, written in this way, meant to evoke all the, right notions to a control engineer, has a nice thermodynamic interpretation where we think about two sources of cost. One is the entropy, right? That's precisely the effort needed to take the reference process and nudge it towards some other process law. And the other one is, you can think about as energy, expected energy, which is your terminal cost, right? Because why are you doing all this controlling? You're doing it so that when the process stops at t equals 1, you obtain some low expected cost. And the variational principle basically says that the minimum free energy is exactly obtained at the optimal control U star, which has an explicit form in terms of the characteristics of the original reference process, and it's equal to precisely minus log of this expectation. Right. So this was our idea of how you would use diffusions for generative modeling. And it's based on very, very, very old results going back to early 1930s. This idea of Erwin Schrödinger, who was interested in understanding certain problems in the interface of quantum and classical physics. It was formalized by Hans Vollmer, among others. But this is the idea, stated in modern ways. So Schrödinger was interested in the following problem. Suppose I have a bunch of particles that are sitting, let's say, at the origin. And then at t equals 0, they start diffusing. Right, so your null hypothesis is that they're just undergoing regular diffusion, which is described by the heat equation or the diffusion equation. And under that hypothesis, if you were to look at the histogram of their positions at t equals 1, it should look Gaussian. Right, because that's what Brownian motion, the marginal distribution of Brownian motion is Gaussian. And the variance is proportional to time. So if you look at the histogram of the particles positions at t equals 1, you should see a Gaussian. But suppose you don't. Suppose you look at the histogram, it actually looks something different. It has multiple modes, or whatever. Maybe it actually it has skewness and other features. So given that, you postulate that, well, there's some force that's shifting the trajectories, that's nudging them away from the Brownian motion, and we want to explain this in the most parsimonious way. And one way to explain that is to say, okay, this force has to use the least amount of energy, and guarantee that at t equals 1, I actually end up with some probability measure mu instead of the standard Gaussian. That would have been true under the null hypothesis. I mean, Schrödinger didn't formalize it exactly like this, but this was the intuition that he had, and it was formalized using ideas from stochastic calculus by others much later. And these are not new results. It's just that in our case they follow very cleanly from this control formulation. So here the first claim is that for any control, let's consider all possible controls, all possible prescriptions of these forces that give you your target distribution at t equals 1. And then you can actually show that there's a lower bound on the control effort needed to do this. And this lower bound is given by the KL divergence between the target and the Gaussian. And it turns out that there is a control that actually achieves this exactly. And it looks like this gradient with respect to x of log of q1 minus t f of x. So let me describe what's going on here. Qt is, this is called Euclidean heat semigroup. And what you're doing is you're taking a function f, and you're convolving it with a Gaussian, right? A variance t. So this is what would happen if you were to look at the average of f when you shift the input x by a Gaussian and taking the expectation. So this actually, if you look at the form of this, this looks exactly like the time reversed score function, and that's exactly what that is. Except that the process you're reversing is just ordinary Brownian motion. You're just running Brownian motion backward in time. And okay, so this gives you an idea of how you could, in principle, generate samples from some distribution. You just need to mimic this Vollmer drift. Again, like I said, we were not thinking about more sophisticated example, that's the basis of denoising diffusion, but this is really the same idea. But the other thing that you might want to ask is something about variational inference, because we're dealing with, sorry, I'm just trying to see how, okay, 15 minutes. We're dealing with generative models. So suppose now we do have some parameter theta, and we would like to approximate the log likelihood of some observations y1 through yn, right? And this log likelihood is given by this kind of a thing, this negative log likelihood. And it turns out that you can basically express this log likelihood as a minimum free energy. This is basically variational Bayes, but reinterpreted in the context of diffusions, right? So the point is that any control U actually gives you a variational upper bound. So if it happens that you can come up with some parameterized class of controls for which you can easily compute or approximate these expectations, then you get a variational bound, and then you can, in principle, parameterize these controls by some other parameter, right? So if you've seen these kind of things, there's typically going to be the latent parameter theta that you're interested in, and then there's some recognition density that has some other parameters that you do gradient descent on, and that's exactly what you could do here. But we didn't really do too much with this. We were really interested in the sampling problem, right? So we wanted to know how expressive these kind of diffusion models are. And the expressiveness question is, well, suppose I have a Brownian motion. So I start at 0, and at t=1, I get a sample from a Gaussian. So I can get samples from other distributions, again, by adding a drift and steering this process towards some other distribution. And we already know that under some regularity conditions on the target distribution, we can do this exactly with minimum control effort, right? So this control basically uses up the least amount of energy, and in fact, that least amount of energy is equal to the KL divergence between the target and the Gaussian, right? So we could do this exactly. We could call it non-parametric sampling because, look, there are no parameters here. You give me f, which is the density of mu with respect to the Gaussian, right? So just take the density of f divided by the density of mu divided by the density of a Gaussian. That's what you get, right? So you can achieve this with minimum control effort exactly. Now, obviously, with generative modeling, this is the same idea as with approximating functions by neural nets. We settle for some approximation error, but what we buy is an easier time computing this drift. Right, so we want to have a function b that depends on the current state and time, and this function b should have some parameter theta, and this parameter, think about it as weights. These weights are time invariant. So the input to this neural net is x and t, just like you see in configurations like UNet for diffusion models, and you want to find theta in such a way that, let's say, this mu hat is what you get using this process, and it should be close to the target in KL divergence, right? So the interpretation is you can think about extending this, universal approximation of functions by neural nets to sampling, right? So this was really the motivation for that work. And by the way, this is not the same thing as using Langevin dynamics, like Markov chain Monte Carlo, because Langevin dynamics, the idea there is that this is a process that you should run for a long time, and eventually after some burn-in, it'll mix and hopefully converge to a sample from the target distribution up to some accuracy. This guarantees a sample, an exact sample in finite time, if you use the proper drift, right? So what we're trying to do is we're asking what could happen at t=1, right? So this is and this was the kind of, like I said, probably the first result on the expressiveness of these neural SDEs, right? So I'm going to spend some time actually unpacking what it says. So mu is the target distribution for x1. And then that mu, let's suppose it has a density with respect to a Gaussian. Like I said, think if mu has itself as a probability density, right? You get f by taking that density, the target density, and dividing it by the density of the standard Gaussian. Think about that in the following way. If there were no control, the distribution at time 1 would be a standard Gaussian, right? This is just a likelihood ratio. between the target and the standard Gaussian. And we assume, so we need to make some assumptions on this density. They're not terribly restrictive. You can basically attain them by approximation, maybe additional smoothing or clipping or what have you. But we assume that both f and its gradient, and this is differentiable, are Lipschitz, and f is bounded away from 0. So that's just some notation assumption on the tails of mu, like they should be kind of roughly Gaussian-like. And then we also make this assumption that both f and its gradient can be efficiently approximated by neural nets on any compact subset. So basically that means that, remember, our task is to sample from mu, right? We want to get a random vector that whose distribution is approximately like mu, but the density f of mu with respect to standard Gaussian is a function, and its gradient is a vector valued function. And what we're asking is that both this function and its gradient can be efficiently approximated by neural nets. So our original problem is a distribution approximation. But we, in the process of obtaining this result, reduce it to a question of approximating functions by neural nets. And that's something that we know about, right? But the point is that these assumptions hold. So just, f and its gradient are sufficiently well behaved, and both f and its gradient can be efficiently approximated by neural nets, then for any epsilon, which is your target accuracy, we can approximate this optimal Fulmer drift, which would give me an exact sample from mu, by a neural net, v hat, that takes d-dimensional input and the scalar, which is the time, and generates a vector in Rd. And the size of that neural net is actually polynomial in everything. So at most polynomial overhead compared to the complexity of these neural nets, such that now if I'm going to use this neural net v hat in this process. And notice that here I'm feeding it the current state, and then square root of 1 minus t, which is that's the standard deviation. You can think about that, such that you at time equals 1 you achieve epsilon approximation and KL divergence. So I really don't. I don't think I should have slides for this for the proof of that. It looks kind of complicated, but I can explain what the idea is. So again, the main message is that if you can approximate f, which is the likelihood ratio between the target and the Gaussian, efficiently by a neural net, and if you can approximate its gradient, that you can efficiently sample from that measure by neural SDEs. And the nice thing about this result is that this neural net has parameters that don't depend on time. So in principle, you could train a model that approximates parameters of a neural net. So take a sufficiently large class of neural nets with this b hat, and then do gradient descent on, let's say, log likelihood to find this. I can briefly explain how the construction was for the proof. The construction is really it's obviously not something that you would use during training, which is where you need specialized expertise. Like somebody had to think of, we need to use U-nets because of certain computational advantages. Our approach was a lot more direct and head-on, but and for that reason probably not very practical. And the approach is as follows. So if you look at this optimal Fulmer drift, it's a gradient of a log, which is basically gradient of a function divided by the function itself. And if that function can be itself approximated by a neural net, then its gradient can be computed using backprop. And in fact, the complexity of that, so that means that if a function has an efficient neural net approximation, then its gradient can also be represented by a neural net that's not much larger than the original function. It's literally just taking the idea behind backprop and implementing it using a neural net. The trick, of course, is this expectation, right? Because what you need to do is you need to actually take a function and smooth it out with some Gaussian noise. But what we did is we replaced this expectation by an average of sufficiently many Gaussians that you sample ahead of time. And the idea is if you sample a lot of them, with high probability they'll be bounded. They'll all lie in some ball of some radius that's proportional to the determined by the dimension, and the radius of that ball scales roughly as square root of log of the number of samples. So basically, the point is that you can approximate this average by a neural net whose size is given by the, you essentially have approximate neural nets implementing F. You have a bunch of them in parallel representing this, this Monte Carlo averaging for that gradient. And then, you also need to approximate things like multiplication, division, various arithmetic operations. You stitch it together and you end up with a computation graph. So the point is that you have a computation graph for the Fulmer drift, and each node in that graph is some sort of a neural net. So as long as you can approximate the nodes in that computation graph by other neural nets and keep track of the resulting error, then you'll be fine. So this was the idea behind that result. Like I said, it is stripped down compared to denoising diffusion models, right? But on the other hand, I think it illustrates the main point. And the main point is that once you have an explicit form for the control that you need to add in order to get a sample from your desired distribution, you can ask questions like, well, are these controls structured enough that I can approximate them efficiently by neural nets? And if I can do that, then are the resulting objectives pertaining to training something that we could just run efficiently using gradient descent and backprop? And for example, here I say, well, can fit neural SDs to samples from you using gradient descent with backprop. It would be a version of score matching, right? The corresponding objective would be a version of score matching, again having to do with, and that follows from the Girsonov theorem that I showed you earlier. And of course, again, you can actually express the idea behind both the forward and the reverse processes in denoising diffusions in that same way. In fact, there was a paper by a group of researchers from Germany and Austria that did exactly this. They basically built on some of the same things as we did and our work in order to more or less state that you can interpret the score term that appears in the reverse diffusion process as a control. Okay. So do you want to leave questions? I suppose we can leave questions to the end. I can move on to the second part. So the first part was about distributions. The second part is much more recent. This is the work with Tanya Viravalli, and this is about using these diffusion processes as generators of functions. So it's sort of the idea is that each diffusion process can be thought of as a neural net with some weights, and the weights are random. And once you average out the weights, you end up with a function of the initial condition, and that function should be thought of as this idealized kind of infinitely wide, infinitely deep neural net that you can then make finite by sampling. And that's actually, I'll explain the idea behind this with reference to some existing work. So this was, so Tanya presented this at the conference on learning for dynamics and control in Philadelphia this summer. Okay, so let's talk about, let's get back from distributions to function approximation, which I mentioned earlier, but it's good to revisit this. So suppose we have a sigmoidal activation function. Unfortunately, these are not deep nets at all. This has one hidden layer, right? So we have a sigmoidal activation function, and then the approximation theorem says that for any continuous f, and any compact domain, you can approximate this f by one hidden layer neural net, such that the number of nodes, notice here, it scales pretty badly with epsilon, right? It's exponential in a dimension, but you can guarantee any desired accuracy, right? So uniform norm approximation of this f by f hat on a desired compact set. And this is exactly, when we talk about cursive dimensionality, this is exactly it. It's that, you could do this, but the number of neurons you need scales awful, right, with the dimension, right? So number of neurons you need to get accuracy epsilon grows exponentially in D, And you can't really do better without assuming more than continuity. Right? So, and in fact, there are various lower bounds that say that if the only assumption you make on F is continuity, then you cannot beat this. So there was a breakthrough by Andrew Barron, who actually at the time was a faculty member in the Department of Statistics here. Now he's at Yale and has been at Yale for a long time, in 1993. And you can summarize it like this. So instead of a finite neural net, let's consider one with a continuum of neurons. Right, so we have our activation sigma, but let's draw both the outer coefficients, the weights and the biases from some probability measure, right, and just sample from it, right? And so if your function has this continual representation, then you can basically approximate it by a finite neural net, right? So F looks like this, but Fn hat is finite, has n neurons, and you can approximate it by Fn hat, where the approximation error squared scales as 1 over n. And notice that this gives you the reduction from this exponential growth that applies for continuous functions to something that looks like this. So squared in 1 over epsilon for functions in the so-called Barron class. So Barron class is a class of functions that really have representations like this. I should say that there's a bit of a fine print here in that this constant C mu may actually scale exponentially with dimension, but at least, but you can actually compare the orders of magnitude. It's still much better if only this constant depends exponentially on dimension. Ordinarily, you would have n to 1 over d here, right? Which would be actually pretty bad. And the proof is really by probabilistic selection. What you do is because your original function looks like this, as long as you know this probability measure, you can sample from it. You can get IID samples, and you can see that each of these is an unbiased estimate of f at a given point x. And then you control its variance. The variance scales as 1 over n, and that's exactly what you get here. And this is based on something that's now referred to as Moiray's empirical method, but the idea goes back to Andrew and to Lee Jones, who had an interesting greedy algorithm for approximating neural nets. Okay, so what's the idea behind this Barron class? So Barron's main insight really was he turned the whole thing around. Right? Previous results were like, we want to approximate continuous functions by neural nets. Well, cursive dimensionality shows up, and this is it is what it is. Barron's insight was, well, okay, but what if I demand more than continuity? What if I specifically ask what kind of functions can be efficiently approximated by neural nets with sigmoidal activations? And he showed that a particular class that allows you to approximate them efficiently consists of functions whose Fourier transforms, defined like this, are sufficiently well behaved that if you look at sort of quote unquote first moment of or the correlation of the Fourier transform with the frequency vector, this quantity is finite. And it turns out that if a function is in this class, you can approximate it efficiently. Everything is nice. But you cannot really have a necessary and sufficient condition for testing when a function belongs to this class. But you can say a lot of this kind of class. It's a rich class of functions. It's closed under translation, convolution, scaling, composition with analytic functions. A Gaussian, for example, is in that Barron class. And then a corresponding constant depends nice on dimension, etc. But it's kind of an implicit characterization that if a function has decent behavior in frequency domain, then right, because this tells you kind of the rate at which its Fourier transform falls off as you go farther out into the frequency domain, then you can efficiently approximate it, right? But the thing is that we can actually make this abstract, right? Because this idea really works for any function that can be represented as an average like this. So think about the sigma as some quote unquote activation function. It doesn't have to be sigmoidal. So you just fix sigma ahead of time. You say, okay, if I average weights according to some mu, I can obtain functions that look like this. It's going to be a large class of functions. You can think about this as sort of a closed convex hull of these sigmas. And then you can just sample IID from that. And as long as you have finite second moments, then you get this kind of a 1 over n squared norm approximation. And by the probabilistic method, at least one realization of these weights exists such that you can have a finite combination of these terms and obtain an approximation like this. Right? This is really the idea behind random function approximation. So in our case, what we're interested in is actually taking diffusion processes and using them to generate this randomness, right? Because why not? Right, imagine that what I have is a diffusion process with some drift f and diffusion coefficient g, and think about these as quote unquote, maybe these are neural nets. But the point is that this Brownian motion that drives the diffusion process generates a random trajectory that I feed with my input to the function, right? And at a time capital T, I stop, and then I compute some function of that state. In this case, let's even take a linear function. So I just project it onto some fixed vector. And so the function I'm interested in is really this expected value of this W transpose xt little x. So xt little x is the indication that what I'm doing is I have a diffusion process that starts at little x and runs for time capital T. So basically, you can think about this as kind of an analog of what Barron was suggesting. What you do is you have an activation function. Again, you can think of some sort of a structured nonlinearity, which now looks like this. It's my vector of, you can think about outer weights that you take an inner product of that with the outcome of this diffusion. Right, and so we're interested in really in this variance, right? Because if we want to approximate this f by something finite, then we're interested in this variance. So notice that what I'm doing here is using a diffusion process as a mechanism for generating random functions, right? And of course, here you can actually show that for expressiveness, the dependence of this function on the initial condition x has to be nonlinear, right? And in fact, the only way to have this linear is if this process is Gaussian, and that would require f of x to be linear in x and g of x to be constant. In that case, all I'm doing is I'm just sampling from a multivariate Gaussian. But if I choose f and g's from some nice classes, let's say maybe f is like a one-layer neural net and g is a constant matrix, then I can hope to generate much more interesting nonlinear functions. But this is the idea. Okay, so and it turns out that really what you're interested in is a class of densities that can be generated by a diffusion process, right? Because what you're doing is you're taking a linear function of y, where y is the state of that diffusion process at time capital T with the initial condition little x. So you're interested in this variance. And so all that talk about Brownian motion and paths and whatnot really makes it complicated. The real thing is that this diffusion process has a transition density, right? So if I started at time, if I started at x, and I'm asking what's the conditional distribution of y at time little t, then under some assumptions on f and g, this diffusion process will have densities. So for example, if f is 0, right, there's no drift, and g is, let's say, 1, then this is just a Brownian motion, and these densities are Gaussian. In which case, like I said, all you're really doing is sampling from a multivariate Gaussian. But if f is nonlinear, and g may have some structure, then this density is going to exist, but it's going to depend in a nonlinear way on x. And this is what we're hoping to characterize. Right, so really what we really need is bounds on this transition density. And this is actually an old problem, not only in the theory of diffusion processes, but also in theory of partial differential equations. Because if you're given a PDE, a lot of times what you want is some estimates on a solution, because PDEs are complicated. There is no general theory of partial differential equations like there is for ordinary differential equations. You really have to many times just isolate some broad class of PDEs and make statements about it. And it turns out that for a broad class of PDEs known as parabolic PDEs, you can actually get estimates on their solutions. And a lot of times these estimates look kind of Gaussian. And the problem is that the various constants in those estimates may scale poorly with various things like dimension. So you want a more refined characterization. As it turns out, there was a remarkable result by Shujin Shi in 1991, who gave pretty sharp bounds on this density. So the assumptions that both f and g are Lipschitz. So let's suppose your f is like a hyperbolic tangent, so it's Lipschitz, and g is, let's say, constant and will hold. But you also demand the diffusion to be what's called uniformly elliptic, meaning that if I take G and I form this matrix GG transpose, and you can think about it as like a local covariance matrix for the diffusion process, I want the eigenvalues of that matrix to be bounded away from 0 uniformly in X. Which is so it really singles out class of diffusions and rules out things called degenerate diffusions, where this matrix GG transpose may have 0 eigenvalues. But it's okay. But the nice result is that under the above assumptions, the density, right? So you start at X, deterministic point. This is a conditional distribution of the position of diffusion at time capital T, given the initial X. And it turns out you can have upper and lower bounds that look kind of Gaussian. But the interesting thing here is that you have a certain functional that depends on your time T, but also depends on the initial point and on the final point. And this functional can actually be characterized. So this is what it looks like. Imagine that what I do is I pretend that I don't have a stochastic differential equation. Imagine that I have a deterministic system where I replace the noise by some control input u, right? So now I have just a differential equation. C of t is a vector in Rd, u of t is a control at time t. I just keep the same drift and f and the same diffusion coefficient g. Right, so this is now a control system. Just like in the case where I was saying you could use the drift to steer the diffusion process towards towards a desired distribution, here you can use the control process to make the system, hopefully if you can do it, well, g is positive definite, so you can, to steer it from a given initial point x at time 0 to a given terminal point y at time capital T. You have to obey this dynamics, and you have to minimize the control effort. Remember, we talked about this, using control effort to achieve a given objective. It's a similar thing here, but here the idea is that I replace the noise by something I can myself control, and I'm asking for the smallest energy of the control that transfers a given point x to a given point y. And this functional, yes.
We're over time, so.
We are?
Yeah.
Oh, you're right. For some reason I thought it was 12. Okay, never mind. Okay, so then it's okay. I'll just tell you that we have upper. Somehow I lost track. I thought I was talking until 12:45. Sorry about that. Yeah. The point is that we can actually get upper and lower bounds on that control effort, which are reasonably tight. So this is a lower bound that gives you an upper bound on the density. The point is that the functions that are realizable by diffusion models roughly look like this, and for expressiveness, you can actually make this a nonlinear function of x. And sorry about that, just completely lost track of time.
Lauren has to leave, so I'll MC for a minute. A quick question, so before we break for lunch.
Yeah.
So a lot of the analysis relies on SDE theory, but in practice, when they use diffusion models, people discretize them.
Right.
So is there anything that sort of connects the two and sort of figure, can you say anything about what the errors are and
for discretization? So that's actually an interesting thing. It seems there's actually a lot of literature on numerical approximation of optimal control problems for diffusions. But the thing is that what's happening with diffusion models now, I think this has the potential to transform what control theorists were doing. So numerical methods that control theorists were using, and you could analyze them, they don't scale. And so with diffusion models, because you're basically solving these stochastic control problems, the methods that have been developed for inference and for various architectures that approximate these functions are rather efficient and scalable. And so I think this is actually a completely new direction. This is using the ideas and techniques developed by practitioners and theorists in machine learning. We can actually now go back and re-examine some of the work in control. So I think that's also a nice application.
Thank you.